Hello, Royals. For lesson 6.4, we were expected to be able to evaluate logarithms. One of the dangers that students get into with logarithms is they only fixate on them being able to be written in exponential form. So say I give you log base, 2 of 32. Then students will set log base 2 of 32 to be x, and then they maybe memorize that this can be written in exponential form as 2 to the exponent x equals 32. And it works out okay in most situations. They then are solving an exponential equation by setting both sides equal to the same base and then equating their exponents. I would strongly suggest that we try to read this in English as the exponent that one places on a base of 2 to receive the power 32, and try real hard to be able to just evaluate it by sight or maybe with a little bit of trial and error. Because when we get more complicated logarithmic expressions, writing it in exponential form is going to become problematic. Let's look at some challenging examples from our homework or our lesson where writing it in exponential form is really going to slow us down, or if the expression's already written in exponential form. So I think we tried this in the lesson. Try reading this one in English as, I'm just going to write it out for you. 4, comma, raised to the exponent that, comma. So here's 4, and then there's a superscript, so I know that's an exponent. But the other reason why I know this is an exponent is because it's a logarithm. So that right here is the exponent that, if it's placed on a base of 4, would yield a power of 64. So try reading this in English, because we're not quite done yet. 4 raised to the exponent that you would place on a base of 4 to receive the power 64 is going to give you 64, right? Now we're starting with a relatively easier example here because we can evaluate log base 4 of 64. Let's write it like this. Let's say 4 to the exponent log base 4 of 64 is going to be, well, let's just keep the 4 there, and then ask yourself, what exponent do I place on a base of 4 to receive the power 64? The answer is 3. But what do I do with that exponent of 3? I place it on a base of 4. I put on a base of 4 the exponent that I would put on a base of 4 to receive the power 64. So guess which power I receive? 64. Now, sometimes students will comment and say, I don't get it, that doesn't make sense. But like, this is the definition of sense. All you need to be able to do is follow the language. And it would be ridiculous to think that the answer is anything else. Imagine the exponent that you would put on a base of 4 to receive the power 64. Now put it on a base of 4, and you will receive the power 64. Let's try another. Similar numbers. 7 to the exponent log base 7 of 64. So this one might be a little bit more challenging because I don't know the exponent I place on a base of 7 to receive the power 64. It's some number between 2 and 3, I guess. Probably closer to 2. Let's try it again in English. Let's say, imagine, starting up in here. Imagine, 1M. Imagine. Picture the exponent you would place on a base of 7 to receive the power 64. Okay? Make sure you're using keywords when you're doing this. You don't want to say the number that you put on the number 7 to get the number 64. You also want to avoid the word answer, because there's many different answers to many different questions here. Picture the exponent you would place on a base of 7 to receive the power 64. Now place that exponent. Where? On a base of 7. You will receive the power 64. So 7 to the exponent that you would place on a base of 7 to receive the power 64 yields the power 64. Like, we can try an algebraic proof of this, but it tends to look kind of circular. Let's set, I don't know, u to be log base 7 to the exponent 64. Okay, so I'm replacing this right here with u, basically. Right? Then the original expression becomes 7 to the exponent u. But then over here, let me just rearrange a little bit and write this in exponential form, I suppose. U is the exponent that I would place on a base of 7 to receive the power 64. So when I introduce u to be log base 7 of 64, that means that 7 to the exponent u is 64. But when I replace log base 7 of 64 with u, notice that I get 7 to the exponent u. What do I know about 7 to the exponent u? I know that it's 64. I can do this without solving for u. I don't need to know what log base 7 of 64 is to know what 7 to the exponent log base 7 of 64 will be. Okay. The next two that I have are kind of just for comparisons, for a lead up into lesson 6.5, let's say. Let's look at 3 times log base 2 of 16 versus log base 2 of 16 cubed. I guess the lesson here might be to keep our numbers small. 3 times log base 2 of 16. Log base 2 requires an argument of 16. There it is. That entire exponent is being multiplied by 3. When I say the exponent's being multiplied by 3, that makes me think, because the only thing I've ever multiplied exponents by are other exponents. Well, I know that log base 2 of 16 is the exponent I place on a base of 2 to receive the power 16. That number is 4. And I know that 3 times 4 is 12. Cool. Okay. Over here, this is not log base 2 of 16 cubed. No, this should be read as log base 2 of the cube of 16. The square brackets are not required. That's how it should be interpreted. Okay, if I needed to cube the logarithm instead of cubing the power, I would need to put brackets around the entire logarithm. So let's keep our numbers small here. And I think what I might do here is, instead of writing this in exponential form, let's just try to write 16 as a power of 2. It's kind of what I did over here, except I didn't write it in, did I? Log base 2 of 2 to the exponent 4. I think this gives us one of our other simpler log properties, that log base 2 of 2 to the exponent 4. What exponent do I put on a base of 2 to get 2 to the exponent 4? Well, that's just 4, isn't it? Here, though, I'm not ready to write the number 4 because I'm taking log base 2 of 2 to the exponent 4 cubed. Let's dig up our old grade 9 power law that says to simplify the power of a power, we can keep our base and multiply our exponents. Here, you have 3 groups of 4 groups of 2. If you write this out, it's 2 to the exponent 4 times 2 to the exponent 4 times 2 to the exponent 4. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 groups of 2. Now, I don't know what 2 to the exponent 12 is, but I'm not asked to find what 2 to the exponent 12 is. I also don't know what 16 cubed is. This is another question where we would not need to have access to a calculator. But if you ask me, what exponent do you place on a base of 2 to receive 2 to the exponent 12, the answer is, of course, 12. So just make a note of this fact that these two expressions are equal to each other. It sometimes surprises students that how can you have like a coefficient here and it's the same to having an exponent there. A logarithm is an exponent. The only thing that I can multiply exponents by are other exponents. That means that this right here actually is an exponent as well. Okay. Over here we had to dig up an old grade 9 power law. which I think we should have reviewed. If not, we're going to be reviewing them real soon when we develop our logarithmic power laws. Let's dig up another opportunity. Last one. Let's evaluate 4 to the exponent log base 4 of 6 plus log base 4 of 10. We should be able to evaluate this by hand. We should not require a calculator. We should be able to show our work here. So writing this expression as a log or as in exponential form is problematic because there's more than one expression. Like I could set this equal to x and set that equal to y, but then I'm kind of making a mess of my expression. I'm also not in a position to say, oh, isn't this just like 6 right there? Because the order of operations suggests that I need to simplify my exponent before I raise a base to that exponent. Now, what we need to do here is look at what's happening between our exponents. Our exponents are being added. And then what we need to do is ask ourselves, when would we have added exponents before? And we would have done that in grade 9 when we were working with algebraic power laws, when we had the product of two powers with the same base. We rarely in grade 9 use this rule in reverse like this. We usually said when multiplying two powers with the same base, you keep your base and you add your exponents. So let's try undoing this right here. If my exponents are being added, that means that once upon a time, there was a product of two powers with the same base. Okay, like with the distribution of a division across a difference, it's kind of easier to read in reverse. Notice if you have two powers that are being multiplied with the same base, you are allowed to keep your base and add your exponents. Well, why would we want to do that? Probably because I know what 4 to the exponent log base 4 of 6 is. And I know what 4 to the exponent log base 4 of 10 is. I don't know what exponent I put on 4 to get the power 6, but I know that when I put it on a base of 4, when I put that exponent on a base of 4, I will receive the power 6. I don't know what exponent I place on a base of 4 to receive the power 10, but I know when I take that exponent and place it on a base of 4, I will receive the power 10. I have no idea what 4 to the exponent log base 4 of 6 plus log base 4 of 10 is, except I do. I guess it's 60. Not really guessing. I have determined that it is 60. Okay. I think that language, that reading these in English or whatever language you want to use, but with the appropriate words, base, power, and exponent, is the key to success. So practice those skills. Try it out.